You think you're watching a video right now. You think you're sitting in a chair, staring at a screen, in a room, in a universe made of atoms and matter and space. But here's what you don't know. Einstein discovered something over 100 years ago that shatters this feeling completely. He proved that reality doesn't work the way you experience it, not even close. And now, right now, in 2025, physicists are asking a question that sounds absolutely insane. What if this entire universe is a simulation? Not a metaphor, not philosophy, an actual running computer program. This isn't science fiction, this is what the math is starting to suggest. And by the end of this video, you won't be able to look at reality the same way again. Because Einstein didn't just discover relativity, he discovered that the universe follows rules so precise, so mathematical, so engineered, that the line between real and simulated starts to disappear. Let's go. Let's start with what Einstein actually discovered, because most people get this wrong. In 1905, Einstein published a paper that changed everything. It's called special relativity. You've heard of it, but you probably don't know what it actually means. Here's what Einstein figured out. Time doesn't flow, space isn't empty, and the universe has a speed limit. That last one is the key. Light travels at 299,792,458 meters per second. Exactly, not approximately, exactly. And nothing in the universe can go faster. Now, why does the universe have a speed limit? Think about that for a second. If the universe is infinite, if space is just there, why would there be a maximum speed? What's stopping you from going faster? Einstein didn't answer that question. He just discovered the limit exists. But here's where it gets strange. That speed limit isn't just a speed limit. It's a fundamental contact on reality itself. Because when you try to go faster, something insane happens. Time slows down. Not for everyone. For you. The faster you move, the slower your time passes compared to someone standing still. This isn't theory. We've measured it. Astronauts on the International Space Station age slightly slower than people on Earth. We're talking nanoseconds, but it's real. Einstein proved that time is not universal. There is no cosmic clock. Your now is not my now. And space? Space isn't empty. It's a thing, a fabric. It bends, it stretches. Gravity isn't a force pulling you down. Gravity is the Earth bending space around it, and you're falling into that curve. Einstein showed us that the universe is not made of objects sitting in space and moving through time. The universe is made of spacetime, a four-dimensional structure that can warp, stretch, and break. And here's the part that should terrify you. Einstein's equations are perfect. They predict the orbit of Mercury down to the arc-second. They predicted black holes before we found them. They predicted gravitational waves 100 years before we detected them. The universe doesn't approximately follow these rules. It exactly follows them, down to the 15th decimal place. Now ask yourself, why? Why would a random universe follow mathematical laws so precisely? Einstein once said, "The most incomprehensible thing about the universe is that it is comprehensible." He meant, why does math work? Why can we write equations that predict reality? Unless reality is math. Unless the universe isn't made of stuff, it's made of information. And if it's made of information, then what's the difference between this and a very, very sophisticated program? Now, Einstein gave us relativity. He showed us reality is weirder than we thought, but he didn't know how weird it would get. Because in the 1920s, physicists discovered something that broke Einstein's mind. They discovered quantum mechanics. And quantum mechanics doesn't just say reality is weird. It says reality might not exist when you're not looking at it. Let me show you what I mean. In 1927, physicists did an experiment called the double-slit experiment. Here's how it works. You take a single electron, one particle, and you fire it at a wall with two slits in it. Common sense says the electron goes through one slit or the other. But that's not what happens. When you're not watching, the electron goes through both slits at the same time. It creates an interference pattern on the other side, the kind of pattern you only get from waves, not particles. Okay, that's weird, but here's where it gets insane. When you put a detector at one of the slits, when you try to see which slit the electron goes through, the interference pattern disappears. The electron suddenly acts like a particle again. It goes through one slit. The act of measuring it changes what it does. Not because you disturbed it, not because your equipment is clumsy, because before you measure it, the electron doesn't have a position. It's in a state called superposition. It's both here and there. It's potential. And when you measure it, when you observe it, reality collapses into one outcome. Einstein hated this. He said, God does not play dice with the universe. But the universe didn't care what Einstein thought, because every experiment since 1927 has confirmed it. Reality behaves like it only renders when something is looking. Now stop and think about that. Think about video games. When you play an open-world game, let's say Grand Theft Auto or Minecraft, the game doesn't render the entire world at once. That would take too much computing power. Instead, it renders what's on your screen, what you're looking at. The rest of the world? It's still there in the code, but it's not being computed. It's just potential, data waiting to be loaded. And when you turn the camera, the game renders that part of the world. The universe works exactly like this. When you're not looking at something, quantum mechanics says it doesn't have definite properties. It's in superposition. It's unrendered. When you look, it collapses. It loads. This isn't philosophy. This is what the experiments show. And it gets even stranger. There's something called the quantum Zeno effect. If you keep observing a quantum system, if you keep measuring it, it stops evolving. It freezes. It's like pausing a simulation by constantly checking its state. Or take quantum entanglement. Two particles can be connected in such a way that measuring one instantly affects the other. Doesn't matter how far apart they are, light years away. It happens instantaneously. Einstein called this spooky action at a distance. He thought it was impossible, but we've tested it. It's real. And here's the thing, in a simulation, this isn't weird at all. If two particles are both part of the same code, the same data structure, then changing one changes the other, instantly, because they're not really far apart. They're connected at the level of the program. The universe is acting like information, not like matter, like data being processed. Physicists have even calculated something called the Bekenstein bound, the maximum amount of information that can be stored in a given volume of space. The universe has an information limit, just like a hard drive. So here's where we are. Einstein showed us the universe has rules, strict mathematical rules. Quantum mechanics showed us the universe only renders what's being observed. And now physicists are starting to ask, what if these aren't just laws of physics? What if they're optimization strategies? What if the universe is conserving computational resources? All right, so far we've talked about physics, Einstein's relativity, quantum mechanics, the strange rules of the universe. But now we need to talk about the argument that made physicists sit up and pay attention. In 2003, a philosopher at Oxford named Nick Bostrom published a paper. It's called "Are You Living in a Computer Simulation?" And it presents a logical argument that's almost impossible to refute. Here's how it works. Bostrom says, assume three things are possible. 1. Civilizations can reach a level of technology where they can run realistic simulations of conscious beings. 2. Advanced civilizations would want to run these simulations, maybe to study their ancestors, maybe for entertainment, maybe for research. 3. If both of those are true, then advanced civilizations would run lots of simulations. Not just one, millions, billions. Now here's the kicker. If billions of simulated universes exist, and only one real universe exists, then statistically, you're almost certainly in a simulation. Think about it. If there's one real universe and 10 billion simulated ones, the odds that you're in the real one are 1 in 10 billion. Bostrom's argument is, either civilizations never reach that level of technology, or they reach it and choose not to run simulations, or we're in one. And here's the thing, we can't rule out any of those options. But let's focus on the third one, because that's where the physics gets interesting. If we're in a simulation, what would we expect to see? We'd expect the universe to have rules, computable rules. Check. Einstein's equations are perfectly mathematical. We'd expect a speed limit, because the simulation can't process information faster than a certain rate. Check. The speed of light. We'd expect a smallest unit of space and time, because the simulation would run on discrete pixels. Check. The Planck length. 10 to the negative 35th meters, the smallest meaningful distance in physics. Below that scale, space-time itself breaks down. It's not smooth, it's grainy, like pixels. We'd expect the universe to only fully render what's being observed, to save on computational power. Check. Quantum superposition. We'd expect information to be conserved, because in a program, data isn't destroyed, it's transformed. Check. The laws of thermodynamics. Information is never lost, even in black holes. Now, none of this proves we're in a simulation, but here's what it does prove. The universe behaves exactly like a simulation would behave. And that's not something you can just ignore. In 2016, a team at the University of Washington proposed a test. They said, if we're in a simulation, the simulation must have a lattice structure at the smallest scales, a grid, and that grid would leave a signature in the distribution of cosmic rays. We haven't found that signature yet, but we're looking. In 2017, a physicist named Silas Bean calculated how much computing power it would take to simulate the observable universe down to the quantum level. His answer? Impossible with any foreseeable technology. But here's the thing, the simulation doesn't need to simulate everything. It only needs to simulate what's being observed, just like a video game. And suddenly, the computing power becomes possible. Elon Musk has said publicly, the odds that we're in base reality is 1 in billions. Neil deGrasse Tyson puts it at 50-50. These aren't random people. These are people who think about the universe for a living, and they're taking this seriously. So let's go deeper. Let's talk about what a simulation would actually look like from the inside. Okay, let's say we're in a simulation. What would that actually mean? First, it doesn't mean we're not real. If you're conscious, if you're experiencing this moment, then you're real. To yourself at least. A simulated person is still a person. But it does mean something profound about the nature of reality. It means the universe is not fundamental. There's something beneath it, something running it. Let's call it the substrate. And here's where it gets mind-bending. If we're in a simulation, then the laws of physics aren't laws of nature. They're rules of the program. And rules can be changed. Think about the Matrix. In the Matrix, Neo learns to bend the rules. He can dodge bullets, fly, stop time. That's fiction, but the concept isn't crazy. If you're inside a video game and you learn to hack the code, you can do things that are impossible according to the game's normal rules. Now, we obviously can't hack the universe. Or can we? Because here's the thing, we've already found glitches. Quantum tunneling, for example. A particle hits a barrier it shouldn't be able to pass through. But sometimes it does. It just appears on the other side. How? It tunnels through by briefly violating the law of energy conservation. The universe allows it because of the Heisenberg uncertainty principle. For a split second, the rules can be bent. Or take vacuum fluctuations. Empty space isn't empty. Particles pop into existence out of nothing, then disappear. They violate the conservation of energy, but only for a moment. It's like the universe is running on a clock cycle, and between ticks, anything can happen. Then there's quantum entanglement again. Instantaneous connection across any distance. In a physical universe, this is impossible. Information can't travel faster than light. But in a computational universe, it makes perfect sense. The two particles aren't really far apart. They're both variables in the same data structure. Changing one updates the other instantly because they're part of the same object in memory. These aren't just strange phenomena. They're behaviors you'd expect from a computational system. Now let's talk about consciousness, because this is where the simulation hypothesis gets really uncomfortable. If the universe is a simulation, are we being simulated too? Or are we the observers for whom the simulation is running? There's a concept called the Boltzmann brain. It's a thought experiment. It says, given enough time, random quantum fluctuations could spontaneously assemble a functioning brain, complete with memories, thoughts, and the experience of consciousness. That brain would exist for a brief moment, think it's a person with a history, then disintegrate. How do you know you're not a Boltzmann brain right now? How do you know your memories are real and not just random configurations of particles that happen to form a brain that thinks it has a past? You can't. Now apply that to the simulation hypothesis. How do you know you're not an NPC, a non-player character, a background character in someone else's simulation? You feel conscious, you feel real, but so would a sophisticated NPC if it were programmed well enough. And here's the thing, if consciousness is computable, if it's just information processing, then there's no difference. A simulated consciousness is just as real as a biological one. Because what is your brain? It's a biological computer, neurons firing, signals processing, information integrating. If you can simulate that perfectly, you've created consciousness. The philosopher David Chalmers calls this the hard problem of consciousness. Why does information processing feel like something? Why is there an inner experience? We don't know, but here's what we do know. Your experience of reality is not reality itself. It's a model your brain creates. Light hits your retina. Signals go to your brain. Your brain constructs an image. You're not seeing the world, you're seeing your brain's interpretation of electrical signals. Sound? Same thing. Touch? Same thing. Everything you experience is a simulation your brain is running. So in a sense, you're already living in a simulation. The question is there another layer beneath that? So where does this leave us? Is there actual evidence we're in a simulation? Or is this all just speculation? Let's look at what physicists have found. In 2012, a team of physicists at the University of Bonn did something remarkable. They created a simulation of the universe. Obviously not the full universe, just a tiny piece. They simulated the strong nuclear force, the force that holds quarks together inside protons and neutrons. And here's what they found. When you run a simulation on a lattice, a grid structure, it creates specific patterns in the energy distribution, signatures, artifacts of the grid. And they said, if our universe is running on a grid, we should see similar signatures in high-energy cosmic rays. We haven't found them yet, but the fact that they're testable is huge, because for the first time, the simulation hypothesis isn't just philosophy, it's science. Then in 2017, a paper was published in Scientific American by physicists at MIT. They proposed that black holes might be cosmic GPUs. They argued that black holes process information at the maximum possible rate allowed by physics. And when you calculate the information content of a black hole, you find something bizarre. All the information is stored on its surface. Not inside, on the surface. This is called the holographic principle. It's like a 3D movie being projected from a 2D screen. The entire universe might be a hologram, a three-dimensional projection of information encoded on a two-dimensional surface. Why would the universe work like this? Because holograms are efficient. They store the maximum information with the minimum resources, just like a simulation would. Now let's talk about the Planck length again. 10 to the negative 35 meters. That's the smallest possible distance in physics. Below that, space and time don't make sense. They break down. Why? In normal physics, there's no reason for a smallest length. Space should be infinitely divisible. But in a simulation, there has to be a pixel size. The simulation runs on a grid, and the grid has a resolution. The Planck length might be the resolution of the universe. Then there's something called the Bekenstein bound. It says, there's a maximum amount of information that can exist in any region of space. If you try to pack more information in, the region collapses into a black hole. This is a hard limit. Just like a hard drive has a maximum capacity, the universe has a storage limit. Why would a physical universe have a storage limit, but a simulated one? Of course it would. And here's one more thing, the fine-tuning problem. There are about 20 fundamental constants in physics. The strength of gravity, the charge of an electron, the mass of the Higgs boson, and they're all perfectly balanced. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it was slightly weaker, stars wouldn't form at all. If the electromagnetic force were different by even 1%, atoms couldn't exist. The universe is balanced on a knife's edge. Why? One explanation, the multiverse. There are infinite universes with different constants, and we happen to be in one that works. Another explanation, design. Someone set the parameters. Both explanations sound crazy, but the simulation hypothesis gives you both. If we're in a simulation, the constants are parameters. Someone set them, and there could be millions of other simulations with different parameters. The fine-tuning problem disappears. Now, does this prove we're in a simulation? No. But it explains a lot of things that are otherwise very, very hard to explain. So, are we in a simulation? Honestly, we don't know. And that's the most honest answer anyone can give you. But here's what we do know. Einstein proved that reality doesn't work the way you experience it. Time doesn't flow. Space isn't empty. The universe has limits. Quantum mechanics proved that reality behaves like it only exists when observed. Mathematics proves that the universe follows laws so precise they look like code. And the simulation hypothesis explains all of this in a way that's uncomfortable, but consistent. Now you might be thinking, does it matter? If we're in a simulation, what changes? And here's my answer. Everything. And nothing. If you're conscious, you're real. To yourself. Your experiences matter. Your relationships matter. Your choices matter. But the nature of reality, that changes. Because if we're in a simulation, then the universe is not the end. It's not fundamental. There's something beyond it. Maybe it's another universe. Maybe it's a programmer. Maybe it's something we can't even imagine. But it means the question doesn't stop here. Einstein once said, "The most beautiful thing we can experience is the mysterious." He was right. We're living in a universe that looks designed, that behaves like a program, that only renders what we observe. And we don't know why. Maybe we're in a simulation run by a post-human civilization. Maybe we're in a cosmic experiment. Maybe reality is stranger than even that. But here's the thing, you're aware of it now. You can't unsee it. Every time you look at the night sky, you'll wonder. Every time physics reveals another strange rule, you'll ask, is this a law of nature or a line of code? And that's okay, because the search for truth, the willingness to question everything, even reality itself, that's what makes us human. or whatever we are. Einstein didn't just give us relativity, he gave us permission to doubt, to question, to look at the universe and say, this doesn't make sense. Let me figure out why. And when you do that, you realize something profound. The universe might be a simulation, but your curiosity, your drive to understand, that's real, that's yours, and no simulation can take that away from you. Welcome to the edge of reality. Now you're standing where Einstein stood, looking at a universe that refuses to make sense, and asking, what's really going on here? Keep asking, because the answers, they're stranger than you think.